So this was our last class, right? Our aquifer and groundwater velocity, right? That was what we are discussing, and this is one example, right? From where, like we were predicting that if there is a contaminant is there, mixture, right? And then how long that contaminant, from example, that is mixed at some point or recharged at one, and how long does it take to reach down gradient, and where you can say there is a drinking water well is there, and you can predict that yes, from here it takes this much time to reach there. So one means that you have identified the source, you cut it off, but you still know that yes, this much time it will be there. Okay. Or like that, you can just have, you can see that yes, this has been started by that time, and we know that yes, still has not reached, and we can have some well which can be dug there to take the your contaminant out of the groundwater. Right? So these are the different advantages are there to find out that what is the application, what is the applications of this velocity, as well as that you need to know that what is this hydraulic head, right? Now that while doing that, these are the assumptions we have made, right? So one thing is that ignore your dispersion or the diffusions of the contaminant, right? And assume the plume moves at the same speed as the groundwater, which means that it's a kind of your plug flow model, or you can one thing could be assumed that say that once that your this whatever the contaminants are, right, or the plume is there, contaminant plume is there, so it is completely absorbed in the water, right? So therefore that it is actually moving with the water. So that could be one thing which is like unlikely. Depends upon what kind of contaminant, and it is unlikely that it will be there. And one thing was that what was ignore the cooling effect of any cooling effect of the drinking water well. Which means that when you are with your this given hydraulic gradient, right? Right, your hydraulic gradient is like that, your water table. So therefore, it is moving there. However, when you are pulling this thing, then how you pull like that? When you are pulling it, there should be some local gradient will be formed there, right? When you are pumping it out, means that it should be like this. So that also gives some error in your calculation. So these are the things we can discuss it in today's class. Means that what is the more realistic picture of contaminant transfer, right? So the first thing is that diffusion and dispersal, right? So diffusion is that when this plume is mixed in the groundwater, right? Then say that if you are seeing from say top, right? This is groundwater, this is rest of the surface. By some means you are actually able to see it like that, right? And at some point, this contaminant, this one is actually mixing up, right? So some point source is there. Then what happens then? That means that your contaminant is very much concentrated, right? And therefore it is likely that this will be as it go in the tank. This is like a more and more like a diffused, right? So the plume is forming, the plume, and and it's a groundwater, that boundary it is becoming like a blur, right? So this is called the diffusion. And not only that, means that the groundwater, your velocity is like, so these are the streamlines, right, from your cylinder, right? However, this diffusion velocity is like depends upon isotropic, and it could be non-isotropic, depends upon the groundwater velocity. However, groundwater velocity is very less, right? So this is like a going in all directions, right? So naturally, here we cannot assume that the plume of the contaminant flow, it is not going with the same velocity with the groundwater, right? So this is called the diffusion. Okay. What is the next one? The dispersion effect. So the dispersion effect is that remember that Darcy velocity or the real velocity that we have discussed. So the medium through which your plume is moving, right? So there is like a porous spaces are there, like this, right? This porosity is not necessary. It is uniform in a cross-sectional area, right? So means that at some portion, it's a huge section. It's a huge section, huge area is there through which when the plume is moving, like it's a tens of meter or something like that through which the plumes are actually moving, right? So it may happen that somewhere it is more porous, somewhere it is less porous there. So from through which this plume that will be having like a different velocity, going at a higher speed, but through which there is like a smaller force, right? Through which it will be going at a lesser velocity, right? So that actually causes the dispersion effect. Dispersion effect. So means that included here. This one simple like a experiment can be done. So you can take a porous medium, right, and through which say this water and this some tracer, which is like acting as a your contaminant there, right? And this is your like a medium. Okay, and here there is this boundary is here from here, through which it actually can go. So seams are there actually, and from here. So this water is coming down. This is for overflow. Right. Okay. And what you are measuring that here the concentration is C0, and here the concentration is C. Right. So now what you can measure, say. Right, so the tracer is a continuously, but the tracer, you mix some tracer and then you measure it with the time. Right, so this is your time, and you see that your this make it like a C by C0, right? C0 where is the concentrations of this tracer and how it is coming in. So first you will be seeing that yes, it's like a clean water that is coming in there. But now, where it will be coming at this position, right? So say if it is at 0, this 1, right? Then if there is a at some time, right? Say the black flow model which is there, makes there. Then after some time, the time which will be like in this medium with the Darcy velocity. You can circulate, then what will happen there? You will be seeing that at some time there will be suddenly a spike, right? Which means that there is no dispersion is there. But if there is a dispersion is there, which is like a very likely to happen, then what we will see? How it look like? Right? Means that there is a this along this across this cross sections, it has like a different velocities, right? Different velocities with which it is coming there because of this medium is there, right? So you will be seeing like this, that it is a at some portion you will be seeing that it is a coming faster, right? So on average it will start coming before this, okay, and then it start increasing, right? More and more it is coming, right? Not necessarily curve will be like that, but more likely to be like that. So then because of this different in velocity across this cross section, which is non-homogeneous, so you will be seeing first on average it is lesser, then after that after some time it is more of the parts this actually comes, which means that there is some portion where it was actually blocked and that seams, whatever the seams type of things that is there, some portion blocked, that actually took some more time to reach. Okay, so that is how you can see that this is the effect of dispersion. Okay. The next is what is the retardation? So retardation means that the medium resistance, right? So the medium can actually also give resistance. In what way? The way is that sometimes this contaminant, part of this contaminant, it is like in that solid, it is absorbed, right? Or adsorbed, right? So that on the surface, that I say like it is contaminant just sits through, right? So it is called adsorption, right? We know that adsorption. Right? So in total, that's why it is called the absorption. Absorption, I mean that is what it is defined here, right? So as contaminants moves through an aquifer, some are absorbed by solids along the way, and some are absorbed there, right? So therefore, this offer a resistance along its path. So it takes like a more time to reach there, right? So if the retardation effect you see that, then it is there, then it will be, you see that it will be at some higher time. It will take longer time to reach there. So this is including the dispersion plus the retardation, right? So retardation factor, this is defined as that the total contaminant in a unit volume of aquifer to the contaminant dissolved in the groundwater, right? So means that if the retardation factor for chlorine ion is 1, which means that all of it dissolves in the groundwater, nothing in the solid. So there is no like a retardation factor is not is imposed on this, right? So all are actually reaching with the groundwater that is going there, right? However, if it is a 5, means that we give it like that 100 by 20. So that's why 5. So 20% is like a dissolved in the groundwater and 80% is dissolved in the aquifer solids. So what happens then that this, you can define it like that, this equal to this average groundwater velocity is, and that is, this means that this much has been absorbed in this water, right? And so the average groundwater velocity and the velocity of the this absorbed material, right? So which is like always found to be like a greater than 1. That's how we can define your retardation factor, right? So this we can define it like that after long time, which in natural it's like that after a long time when there is a all has their natural equilibrium velocity it reaches, then you can define it like that. The amount of reaches equilibrium in the equipment, right? Sorry, equipment. Okay. Right. So two of these these assumptions we have made that we have discussed here, right? Is contaminant transport, the effect of dispersion and your diffusion. Another is like that the velocity of the fluid, which is a different. Now the next one is that the local drawdown or the cone of depressions, right? So you can see here the water table is that this line, dotted line, it is shown here, this broken line, original water table, right? And your groundwater is like a flowing in some directions, right? In this direction or this direction. The thing is that in this scale, that is like a very slope is like a very small, right? So you are almost like seeing it that you see it almost like a flat, right? Horizontal, right? Now, for different reasons we discussed that you can have a well done, right? Which is a pump, and from where you are actually pumping here, right? So pumping means you are actually taking some water out. So when you are taking some water out, means that there has to be some hydraulic gradient is there. And this hydraulic gradient, you can increase your pumping speed, pumping motor. So therefore, which means that there has to be, which should be like a very much high. If you this flow, if you calculate there, it cannot be equal to that hydraulic gradient overall what we have measured. There has to be one local hydraulic gradient to be formed, right? So which is called this drawdown, and which means that what, right? From the both direction, doesn't matter in which direction it is flowing like that. From the both direction, it is taking out the water. So in the both directions, you will be having a drawdown, or in a 3D direction, from there is like a cone is forming, right? If you rotate it, there is a cone is forming. So this is called the cone of depressions that occurs at the near to this pump place, right? Okay. So here also, like we can, this is a very simplistic picture because we do some calculations for the set up a model here. So again, means that you are when you just started pumping, there will be some turbulence, etc. that will be happening, right? It's like a kind of central force, right? So everywhere it is coming down there, so will be some rotations, all these vortex, etc. will be there. So the thing is that you will be getting steady state drawdown when you are reaching equilibrium condition. Right? The pumping has been steady for a long enough time that the shape of the cone is no longer changing, right? And your original water table is horizontal, more or less actually horizontal, right? Not necessarily, but with the data plane, you see that there will be like the slope is really, really small, right? Okay, and the drawdown means that how much it has been reduced, right? When you see that when your well is dug, then it will be on that broken line, at water level. But as soon as you are trying to you are pumping it out, then there is a depression, right? So that drawdown, which is given by that DHC, DHC, or not DHC, that is the flow, that HC, right? Or this B minus HW here, right? Right, this drawdown is small enough. Is small enough relative to the depth of the aquifer, right? So well, and that draws from the entire depth of the aquifer, right? Okay, so the flow is from the entire depth of the aquifer. Okay, not like a from here. Then again the calculations will be wrong. So this is an unconfined aquifer. The picture is shown is an unconfined aquifer, right? And we can extend it for the confined aquifer. I am not showing here, but we can write it here. Okay. All right. Fine. So now you can find out that as equilibrium conditions, all these things are there. So you know that how much water you are taking out from the pump, right? So that is the Q. You can see that, right? At equilibrium conditions, so means that that is equal to, that Q is equal to how much water is coming towards the wall here, right? So here how much water from every side the flow is there, that you can find it out. That is the Q. Of course, Q will be a factor of R, right? As you are, of course, the area is increasing, right? As you are going more distance from the wall, the radius is there, so that area will be there. So of course your Q will be changing, right? I mean the total Q will find it out. Okay, so that is what you can now find it out. Okay, fine. So this is the model equilibrium we can consider, right? Equilibrium consider the one, this cylinder, it is there. The cylinder is drawn at radius r from the center of the well to a radius r. Okay, not radius is not that well radius, at some r you have drawn, and from there you can see this water is from every direction that is rushing into this cylinder, right? Because you are drawing from this up, right? Okay, so Q will be equal to, we can just Darcy's law, simple Darcy's law, you can apply it here, but only the thing is that now that local hydraulic gradient that you have to take it into K, right? So we have K into A dHc by dl, right? So dHc by dl, that is the what the slope is there, right? Okay. And the area is that your cylinder from everywhere it is rushing, that is the area here, and that is twice by r, HC is there. Then after that, because you see that this HC and all these things, it is changing here, so therefore you can find out that what should be the Q. Q is a constant, the pumped well, the pumped well, that is what it is there, from where you are taking it out, right? And that then you can draw two well, right? Here you can see that at HC2 and HC1, and you can see that how much is that your this water table head is there. Fine, you can just, this is like you just dig the well, when the pump is on, dig the well and you can find it out how much is this there, and from there with this two, which is your like this integration constant, in fact, you can find out for this unconfined aquifer, this is how it is relating. K is a constant. For this medium, the K is a constant isotropic. Alright? Okay. Right? So this gives you, what it gives you? You can use it to find out the conductivity, hydraulic conductivity. You know that you can measure HC1, you can measure HC2. You know what is R1, what is R2, and you know that this is your pumped well, this much water is coming out, so you can find out what is your hydraulic conductivity. So one way to find it out. Okay, this is what that one this example you can see it in your book. Right, the same thing. Right, so here you can see that your well diameter is 0.30 meter, and it is the Q is 6,000 meters per day. Right, and so for long enough time it has been pumping it out, and your one observation well is located 30 meters, located, which one is that? 30 meters from the pumped well has been drawdown of 1 meter, right? Okay, and so this is the one. The first well is at a 30 meter. It is drawing down like a 1 meter, right? 1 meter. So when you measure it, because the data plane, and you say that yes, it has been depressed by from the piezometric, that water table head, it has been drawn down by 1 meter, right? And the another well, which is at 100 meter, you will be seeing that that it has that much it is drawn down is 0.5 meter, right? So so you have all of your data, and from there you can find out what is the hydraulic conductivity, right? And this also you can now use it almost, I mean, just for the math. Otherwise you can in fact measure that what is the depression at this well, then what is the estimate drawdown at the well. So without measuring that, you can find the estimate what is the drawdown well. You can use that same formula, but now you know the K, and you can choose any of the well, HC1 or HC, sorry, R1 and R2, but one of them, now one R1 or the R2, that will be your this well radius 0.15 meter. Got it? So it is like at the well also, that means it is depressing. So that is your like this well radius, and from that will give you that how much it is depressed. Okay. Alright, and drawdown now will be like this because HC1, right? This water table height you are finding out. So your drawdown would be that what was your aquifer thickness, which was 30 meter, 30 minus your water table height. Alright. Okay. Right. So in case of your confined, right? I have not discussed yet. Let me draw it here. Right, so in case of your confined aquifer, right? Confined aquifer means that this one is a unconfined aquifer. But the confined aquifer, like this is your this confinement or this space there. Okay. Right. And so this is your well. That of well here. So when it is completely locked between these two surfaces, so in that, I mean, there is no point of like a water table head. In the water table head, you cannot just measure that, right? But instead that, the same thing which you can apply, but now what we know that water table, it was somewhere like this, right? Which is called the piezometric surface. That is the equivalent of the water table in unconfined aquifer. So there would be like a virtually, you have to think that there is a depression in this piezometric surface. So means that had like this confined aquifer become unconfined aquifer, right? So that is what you have to consider here. However, you see that you can, I'm not giving it here. The only thing is that your this B is not changing. right? So when you are calculating this, that K into A is like here. So A is like a only twice by R into B. So right, it is not changing. Right? So expand because this is a virtual thing. This is just a virtual surface. Right? Okay. So it is not changing. Instead, it becomes more easier. A into twice by R into B. Right? And you do that again the same way you do your integrations. And so what does it give you? That it gives you that Q is that twice by kb right, this would be the long R1 by here. Right, because you don't have that dh by h factor, you have a dh by b factor, so therefore that becomes simply ac minus h. Okay. Fine, so this is for your confined amplifier. Right. So all this our discussion. First thing is that you should know that because everything our all this discussion is linked to your environmental pollutions, right? So that's what we started, water pollution there. And groundwater contamination is there. So why, I mean, this well is why? I mean, this well is like that, you can dig it to take out the contaminant, right? So that this velocity, all these things we have discussed there. So, how effectively you can take out the well, or say there is a big area that you have the idea is that this much area is contaminated, right? From here to here, like that. It is contaminated. Now, this plume is like a full, say this class is there, and say this your streamline is also this, I mean, with this it's a transverse, right? Orthogonal, right? So this is your flow like that. So it is actually approaching there, right? It's approaching. Now you would like to take out this contaminant. So the first thing is that you can think that, okay, from here to here, that is your contaminant zone. And let me dig like multiple wells here, right? So here one like that. So, but thing is that how many wells you dig, right? The thing is that it may happen that you can dig like a 3 wells, but instead of you are doing like a 10 wells, so which is not unnecessary like this. Okay. So for that, the next our discussion is that for well, what is the capture, right? So you know that what we discussed, that it will be a local this drawdown is there, a local water is hydraulic gradient that is forming here. So by simplistic like that picture, I mean, you can see that it looks like your this Kepler's law, right? What you read in your schools, right? And like this planet is there, and all these things are there. The satellites are moving, right? So similarly, like that. The streamlines your directions of these flows there, but suddenly there is the pumped well is there. So this will be violating the streamlines there, right? And you can see that this is how the streamlines will look like. Of course, in the equilibrium conditions, it will look like. So, all are like that. The contaminant which is coming from here, this one is like a captured by this well which is situated here, right? So, one envelope we have put. Why did you put that? That we will discuss there, because it will give you. It gives you a better idea to how they formulate the mathematical formula, right? So you can see that it looks like what? It looks like what is the figure? It looks like a parabola, right? So that is how you can invent that you can model it. Like it's a parabolic formula, right? So the envelope you can see, and what does it envelope gives you that. This envelope gives you that for this particular well, this much area from where the contaminant is there, it can take it out, right? It can take it out, all right? So that is what it relates, depends upon what is the power of the pump or how much it can actually, it can take out, the water it can take out, right? So this is called the capture zone, right? Capture zone. So this one is a zone which is it can capture, all right? So anything like is flow lines outside of the capture zone may turn towards this that. Right, so your capture zone is a something like this. So outside the capture zone, which is coming like this, and it will be curved. Then the effect of the pump is not that much strong there, and the dressing velocity that will take care of it. So it will be going like this. So not captured, right? Not captured by this pump. Right. Fine. So. This one, this gives you the what is the trajectory, right? Trajectory of your this envelope. Simple thing, trajectory of this envelope, which is this is given by these equations, okay? Which is nothing but your parabolic equation, right? So the original that I should have put the references here. You can see in the book, right? So original these authors who derived it. Right, so given for this confined equipment, so let us just analyze it, the thing, right? No, derivation, etc., you can do it, I hope, not very difficult thing. See, how we are doing this. First is that the one coordinate system you have to attach it, right? So the coordinate system, what we do, the 0, 0 at the well, and along the streamline, or say along the negative sense of the streamline, x-axis is running there, right? And orthogonal to that, your y-axis is running there. So the y is equal to this q by v, because plus minus, because this side and this side, this side and this side. That's a plus minus v. Where your this one was derived for the what is it? Confined equipment. You can see this is easier actually, right? Because that these things becomes constant. Minus this one tan inverse y by x, or you can what is that? You can actually represent it in terms of this angle which is in the radian. So in that case, tan phi y by x, you can write q by 2vp 1 minus pi by pi, right? Where phi is varying from your 0 to full, right? 0, where it is your x is reaching a very long distance, y is becoming 0, right? X is like infinite, and then where it is like a pi by 2 is like that here at this portion along the y-axis, and it can be like this full circle. So that's why 0 to twice pi, right? What is your total width? The total width, how do you find it out? The total width of the capture zone, you can find it out by putting your x equal to infinity, y equal to 0, right? So that is giving you the only single hub, which will be 2 by twice Vv, and therefore 2 into 2 by twice Vv is a q by Vv, and the width of the capture zone along the y-axis means this one. So you will be getting that there is q by 4 Vv. When you put phi equal to pi by 2, is q by 4 Vv. So 2 into that is there, right? So what does it give you? That if there is a contaminant, that plume width you know, that for a given where in this pumping speed you can locate it, where should I put it? That is the thing. You can put it. Now we can discuss it probably in the next class. Okay. Right, so one announcement is that so I am not here for 30 to 10 November. So 30 means tomorrow, and then November is that this Sunday or next Sunday, right? So I will be here. So naturally, this classes I won't be there. And where I will be, I don't think so that I can take in online class. It will be difficult. So what I am planning that, of course, the thing is that I will email it. So emailing, see my email instructions. So this Friday, of course, no classes are there, and possibly the next Monday. But next Tuesday and next Friday, there will be 2 quizzes. Okay, one quiz will be only the quiz, right? One quiz, the TA they will come here, right? Only 3 people. Maintain the exam room etiquette. So there will be time, the limit will be there, and when the time is up, please give the copies to the team. The first one will be the air pollutions, the meteorological effect, right? Meteorological effect and a Gaussian flow, right? That was the air pollutions. And the other one will be water pollutions up to this point, what we have discussed, right? So 2 quizzes on 2 days, Tuesday and Friday. Similar type of questions, multiple choice or like in this filling the blanks, very short type of questions. Okay. I have to discuss with Professor what to do. So, okay, so that we will discuss. We have time to discuss that part. All right. Some quizzes was also Professor conducted, right? How many quizzes he conducted? 2. How many quizzes was conducted in the Professor Satya's ecology part? 2 quizzes. So I am taking 3. Okay. We will discuss. Arya, present sir. Abhirashi, Devan, Deepak, Kirti, Archie, Saloni, Naina, Bharti, Prabhakar, Rachit, Anushka Patel, Dipanjan, Jaya, Vinayak, Vikash, Ritu, Seduraman, Mukta, Shailesh, Shivojit, Harshit Kumar Rai, Shashank, Avayamir, Ankit, Anushka, Ayush Kumar Singh, Banwari, Pranjal, Richik, Aditya, Aniket, Harshit Kumar, yes sir. Prabhunath, yes sir. Vishal, yes sir. Deepika, yes sir. Divyanshu, Khushbu, Gaurav Mishra, yes sir. Narendra, yes sir. Punit Singh, yes sir. Shivam Vijay, Sarvesh Patel, yes sir. Sanithya, Rohit Raj, Navarkant, Shashwat, Yashasvi, Hamlet, Mohit, Tushar.
मैं मेल कर दिया था अटेंड
हाँ ठीक है, ये 50 कैसे चलता है?
तन्ने कह दिया
क्या हुआ?
तन्ने कह दिया
मुझसे मेरे से बात नहीं हुआ अभी तक ना, तो हम शॉप के साथ